Well, I just got back from oiling up my tractor. Now it's time to talk about linear algebra. When you think about linear independence or dependence, think about redundancy, alright? Are there any unnecessary vectors that don't contribute or don't have to contribute to a vector set? And I'll give you an example of what I mean. So we have a vector here. We know that this vector can span this infinite line. If we add another vector to that, let's say it points like that, well, we can still only span the same infinite line. So we can get rid of one of those vectors and it doesn't change what the span of the set is. But what if instead we add a line that goes off of that line and into a second dimension? Right, the infinite line was just one dimensional, right? Now we're in 2 dimensions. So now we can span this infinite plane. So now that we can span a new dimension, both vectors contribute to the span of the vector set. And we have this sort of a coordinate plane system here based off of those 2 vectors. So we could say that this point here is 1, 0, and this one is 0, 1. Then up here we have 1, 1, right? So we have this coordinate plane system based off of those 2 vectors. And now if we add another vector to this, let's say it points down like this, we can still only span 2 dimensions, right? It's still in that coordinate plane, so it doesn't affect our span at all. It's just a part of the coordinate plane we already had. So we don't need that vector either. But does that mean that that is the linearly independent vector? No, it doesn't. Because we could also get rid of this vector and have these 2 vectors here create our coordinate system instead. Or alternatively, we could get rid of this vector and base our coordinate system off of these 2 vectors. So it's all about redundancy, like what contributes to the span of a vector set. Now let's look at a numerical example. So here we have a vector set. Is this vector set linearly independent? And how can we tell? So linear independence, if we're talking about redundancy, none of the vectors in the set can be represented by any of the other vectors. And we're talking about linear combination here. So we're dealing with 3-dimensional vectors, and we have 3 vectors in our set. So it is possible for this set to be linearly independent, because think about if you're only dealing with 2 dimensions, you only need 2 vectors to span 2 dimensions, right? Think about the standard Cartesian coordinate system, where you have, right, an x-axis and a y-axis. Okay, so there's only 2 vectors that are really contributing to that coordinate system, right? And if you add any 3rd vector, no matter where it is in that 2-dimensional system, they're all going to be able to be represented by the original 2 vectors. Okay, so when we want to find out if a set of vectors is linearly independent, we got to see if any of the vectors in that set can be represented by the other vectors. Well, what we do is called the reduction algorithm, where we look at the first and second vectors, and we say, can the second vector be represented by the first vector? And as you can see, since we have a 0 as our 3rd component of the first vector, no matter what you multiply this vector by, you'll never be able to get a 2 in that spot. Okay, so this vector, 1, 1, 0, would look kind of like this, right? 1, 1, 0, it goes over 1 in the x direction, up 1 in the y direction, and it doesn't go into or out of the page. It's on the page, right? An example of a vector that would be able to be represented by this is any vector along this infinite line, right? So if we had the vector 2, 2, 0, that would look something like this. And as you can see, mathematically, the vector 2, 2, 0 is just 2 times 1, 1, 0. So we could represent that using our first vector. And also, if you multiply by a negative number, you can get anything down here. Right? So the second vector, since it can't be represented by the first vector, does contribute to the span of our set. Now, we look at the third vector. Can this third vector be represented by any combination of the first two? And it turns out, yes, it can. Because remember, we're dealing with linear combination. So we can have the first vector times any scalar multiple plus the second vector times any scalar multiple. And it turns out this third vector is just our first and second vectors added together. Right? 1 plus 1 is 2, 1 plus 3 is 4, and 0 plus 2 is 2. So that shows that our third vector does not contribute to our vector set. So that's a quick lesson on what it means to be linearly independent, and a short example on how to figure out if a vector set is linearly independent. And this is important when you're trying to find the basis for a set of vectors, where a basis is specifically a linearly independent set. And that's our next lesson that we're going to cover tomorrow. So we'll learn how to find the bases of column spaces, row spaces, and null spaces. So I'd highly recommend watching that. If you have a test tomorrow, good luck. I know you'll do great.